Hello students, in today's class, let us calculate the moment of inertia of a ring about some specific axis. So we will look into three different cases. First, we will try to calculate the moment of inertia of the ring about an axis passing through the center of the ring and which is perpendicular to the plane of the ring. So that axis may look like this. Secondly, we will look into the moment of inertia of the ring passing through the diameter of the ring. So you may see it like this. This axis lies on the plane of the ring. The other axis does not lie on the plane of the ring. It is perpendicular to the plane of the ring. It passes through the inside of the ring. And thirdly, we will look into the moment of inertia of the same ring about an axis passing through the tangent of the ring. So let us look into each of these cases. Initially, when the axis passes through the center of the ring, perpendicular to its plane, the moment of inertia will be summation mi ri square. And since this is a continuous mass, we can do integral mi ri square. Here you can see that the distance from the axis towards all the mass points remain fixed. It is always the radius capital R. In the earlier case of a rod, the moment of inertia from the axis towards each of the mass element varies depending on the position of the element. But due to the symmetry of the ring, the shape of the ring, you can see that always the distance from the axis to these mass points remains constant. So instead of different x values, we may fix a single x value or r value. So I is equal to integral over small masses into capital R square, where r is the radius of the ring. Now since there are different mass elements on this ring, we can choose that the mass of each of the element is given by Tm. So the total moment of inertia I will be integral dm r square, where the integration is with respect to mass. So r square is a constant, r square into integral dm. Integral dm is simply the total mass of the whole ring. So that is equal to r square into capital M. So we have found that the moment of inertia of the ring about an axis passing through the center of the ring is equal to mr square. You may also employ summation sign instead of integration here. But since the mass is continuous, it is more advisable to use integration instead of summation. And since that effect does not make any change in the value of I, you can use summation or integration for finding the total mass. Now, having found out the moment of inertia of the ring about an axis passing through the center perpendicular to the ring, now let us try to find out the moment of inertia of the same ring with total mass m and radius capital R about an axis passing through the diameter. In this case, we may use perpendicular axis theorem. Consider two diameters that are perpendicular to each other on the plane of this ring. So AB and CD are those two diameters. And they are perpendicular to each other and they lie on the plane of the paper, plane of the ring. And the moment of inertia about the axis is set. As we have already calculated, it is equal to mr square. And from the equation of perpendicular axis theorem, we have Iz is equal to Ix plus Iy. Here, Ix is the moment of inertia about the BA axis and Iy is the moment of inertia about the CD axis. Now, due to the symmetry of the ring, we have Ix equal to Iy because both these diameters are one and same. They have the same length and distribution of mass. So we can write Iz is equal to 2 times Ix. Since we have already calculated the value of Iz, we may substitute that here. Iz is mr square. So mr square by 2 is equal to Ix, which is same as Iy. So it is obvious that the moment of inertia of the ring about an axis passing through the diameter of the ring is equal to mr square by 2. Now let us calculate the moment of inertia of the same ring about an axis passing through the tangent. So which theorem should you use in this case? Since the axis passing through the diameter and axis passing through the tangent are parallel to each other, we can use the parallel axis theorem. We have already calculated the moment of inertia about this ring through an axis passing through the diameter, which was obtained as mr square by 2. So that is equal to ICM. The center of mass of this ring is at the center due to the symmetry of the ring. Now the total mass of this ring is m, and the parallel distance between these two parallel axes is capital R. The perpendicular distance between these axes is capital R, the radius of the ring itself. So according to the parallel axis theorem, I about this tangent axis is equal to ICM plus mass of this ring multiplied by the distance between the axis square. So this is equal to mr square by 2 plus mr square, which is equal to 3 by 2 mr square. So I about a tangent is equal to 3 by 2 mr square. So we have obtained the moment of inertia corresponding to a ring passing through 3 different axes. First, through an axis passing through the center of the ring, it was obtained as I equal to mr square. Secondly, through an axis passing through the diameter, which is mr square by 2. And thirdly, through an axis passing through the tangent, it is 3 by 2 mr square. So as you can see, when we change the position of the axis, the moment of inertia in fact changes. The difficulty to rotate this body about the axis changes. So I hope these calculations are clear for you. Thank you.